At its physical layer, the internet exists to solve a specific logistical problem, moving data reliably across a vast, partially connected web of switching nodes. For decades, the dominant model for doing this was circuit switching. It operated on a strict requirement. A dedicated physical path had to be fully established between 2 points before a single piece of information could be transmitted. This creates 3 mandatory phases of communication. First is circuit establishment, where intermediate nodes negotiate and lock in the path. Second is the data transfer itself. Finally, the circuit disconnect phase terminates the connection and frees the hardware. By locking down a physical route, circuit switching guarantees quality of service. Quality of service is a networking standard that ensures a specific level of performance, like guaranteed bandwidth. Because the path is dedicated exclusively to one connection, data flows without experiencing any queuing delay at the intermediate switches. However, this architecture struggles with modern computer data, which is highly bursty. When an application stops sending data for a moment, the physical circuit remains open and locked. This results in severe resource hoarding. The network allocates bandwidth and internal switch connections to an idle circuit. If the network reaches its hardware capacity, new users are physically blocked from establishing connections, even if the active wires are completely empty. Circuit switching succeeds in providing absolute predictability, but its failure to efficiently utilize bandwidth makes it unsuitable for the variable, high-volume traffic of digital computing. The engineering response to bursty traffic was datagram packet switching. Datagram packet switching is a routing model where messages are divided into chunks, and each chunk is treated as an independent entity by the network. This diagram shows the core mechanic. Application data is broken down into discrete, self-contained blocks. Because these blocks are no longer traveling down a dedicated pipe, each packet requires its own control information header to reach the destination. This enables statistical multiplexing. Statistical multiplexing is a method where a single communication link is shared dynamically among many users over time, rather than allocating fixed, dedicated fractions of the bandwidth to individual users. Datagrams operate in a stateless environment. The network does not pre-plan a route, nor does it remember previous packets. Consequently, every single packet must carry the full destination address. Because switches evaluate the network individually for each packet, pieces of the exact same message can take completely different paths across the grid. This means they can, and frequently do, arrive at the destination out of order. Datagram packet switching ensures no bandwidth goes to waste, maximizing line efficiency. The trade-off is the loss of predictability and the introduction of a new architectural bottleneck: queuing delay. To understand queuing delay, we have to look past the physical wires and examine the internal hardware of the switching nodes themselves. Looking at this schematic of a circuit switch, we see a control unit and a digital switch. Once the control unit maps the route, the digital switch physically locks an input line to a specific output line, creating a transparent, uninterrupted path for the signal. A packet switch operates differently. It requires input queues to catch incoming data, a centralized switch fabric to route it, and output queues to hold it before transmission. This diagram illustrates packet contention. If 2 input ports simultaneously receive packets, say packets A and B, destined for the exact same output port, the switch fabric can only push one through at a time. The others are forced into a linear queue buffer, forcing them to wait. The physical architecture of the switch determines the nature of the network. A circuit switch guarantees deterministic delay because the path is clear. A packet switch introduces non-deterministic delay, dependent entirely on how many other packets are crowding the buffers. Every node in a network imposes 4 distinct types of delay: propagation, transmission, processing, and queuing. Propagation is the time it takes a physical signal to travel through the wire. Transmission is the time required to push all the bits of a packet onto that wire. This visual plots the precise timing profiles of these models. Focusing on the leftmost diagram for circuit switching, we can see the heavy upfront cost of the setup phase. The call request signals angle downward across the nodes. Before a single byte of user data moves, the network incurs significant propagation and processing delays just to build the route. Now contrast this with the rightmost diagram, detailing datagram packet switching. The data flow takes on a staircase pattern. This happens because datagram switches utilize a store and forward mechanism. Store and forward requires an intermediate node to completely receive and buffer an entire packet before it can begin transmitting it to the next link, compounding the transmission delay at every hop. For massive, continuous files, circuit switching is mathematically faster. The heavy initial setup delay is amortized over the course of a rapid, continuous transfer with zero queuing interruptions. But for very small, bursty transmissions, datagram packet switching wins. The entire data payload can be packetized, transmitted, and received in less time than it takes a circuit switch to process the call request and call accept signals. End-to-end network delay is never a static property of the wire. It is a highly dynamic calculus driven by connection setup overhead, packet sizes, and the physical distances between the switches. Modern networks require both the predictability of a dedicated circuit and the efficiency of statistical multiplexing. The engineering solution is Virtual Circuit Packet Switching, or VCPS. VCPS incorporates the first half of the circuit switching model. It mandates a strict setup phase, actively reserving a specific, logical path through the network switches before any communication is authorized. The second half of the design pulls from the datagram model. The actual payload is still broken down and transmitted as discrete packets, rather than a continuous analog wave. Because the path is predetermined during setup, packets follow the exact same route and arrive in strict order. But because the data remains packetized, the physical wires are not permanently locked, leaving the links open to multiplexing for other virtual circuits. VCPS successfully grafts the traffic engineering capabilities of a telecommunications network onto the burst-tolerant architecture of the Internet. To make virtual circuits function at scale, engineers abandoned full IP address routing in favor of a hop-by-hop mechanic called label swapping. Standard datagram routers are stateless, meaning they must perform computationally expensive lookups on long, complex destination addresses for every single packet that enters the buffer. This slide illustrates stateful routing. Instead of full addresses, routers scan a tiny virtual circuit identifier, or VCI. When router 1 receives a packet bearing VCI 1, the table dictates output to router 2. Crucially, the identifier is swapped for a new one before forwarding. This swapping is necessary because VCI numbers are only unique on a per-link basis. If identifiers were assigned globally, the system would immediately run out of numbers, so the tags must change at every single hop. This label swapping architecture is the bedrock of major telecommunication protocols. It drives ATM, asynchronous transfer mode, a standard that encodes data into small, fixed-sized cells, and MPLS, multi-protocol label switching, which directs data across enterprise networks using these short path labels. While IP datagrams provide the universal language of the Internet, it is the underlying virtual circuits that supply the critical traffic engineering, predictable delay, and isolation necessary to operate global data infrastructure.